Hello everyone, this is a video about the derivation of the one-dimensional heat diffusion equation using control volume analysis. So let's start by considering a large control volume of the size delta x, or big delta x. We need to consider the heat in and the heat out, and we're going to do this by looking at the temperatures. So the temperature in to this control volume is going to be T, and that's going to be a function of x, the position, and T, the time. And the temperature out, I think you'll agree, is going to be the temperature which came in plus some change in the temperature. This change in the temperature can be written as, so we can write this change term as the way that the temperature changes in x, or the gradient, which represents the changing in temperature with the changing in x, multiplied by the change in x. So you'll see that these x's would cancel and you'd be back to this delta t term. We can do the same thing with the inlet temperature gradient. So we can say that the temperature gradient in is delta t by delta x, and you'll agree, I hope, that the outlet temperature, or the outlet temperature gradient, excuse me, is delta t by delta x plus some change in delta t by delta x. And in the same fashion that we wrote the change previously, we can write this as delta t by delta x plus the way that the gradient changes with x in x. So what we're saying here is that the gradient out is the gradient in plus the change in the gradient with x, or the gradient of the gradient in x. And you can see that these x's here would cancel and you'd be left with the original term. So this is all well and good, and it's just to illustrate how things change in the control volume, so that it's less confusing when we go to the differential control volume, which is what we're going to do now. So if we consider another control volume, except this time on a small element dx, with our axis of position x going in this direction. Whoops. That's an x. We can say that the temperature going in is T, which we know is a function of x and T time. And the temperature coming out is going to be that same temperature, but the change in temperature with x, which we're going to write as partial dx, partial dt by x multiplied by the small change in x. As you see, these are analogous, these two bits here, but we're saying it's the partial derivative of t with respect to x, because t, big T temperature, is a function of both position x and t time. And so we're taking the derivative only with respect to x. We're multiplying by that small change in x, and we're saying that the temperature out is the temperature in plus the small change in x times dx. And we can do the exact same thing for our temperature gradient. Now, our temperature gradient we know is dt by dx. That's just the rate of change of temperature with x, or sorry, the change in temperature with x. And our out is going to be that same inlet gradient plus the change of the gradient with x multiplied by some small change in x. And if you follow this through and you differentiate this with respect to x like we've done here, you'll see that this is equal to partial dt by dx plus the second derivative of T temperature with dx multiplied by that small change. Now, what we've done here is we've balanced the heat, or we've balanced the temperature on this control volume. And we're going to say that the area of this control volume here is A, which has units of meters squared. And you'll see why that's important later. Right, so now that we've got our control volume set up, we can start to consider how the heat's going to flow. And we know from our energy balance that the heat in minus the heat out is going to be equal to the heat accumulated. And so we're going to say that there's no heat generation in this control volume. Just to keep things simple, there's no heat generation. So the heat in minus the heat out equals the accumulated heat, and we can also call this the change in heat. So let's start considering what these terms might be equal to. Our temperature in, if you remember Fourier's law, will be equal, or sorry, our heat flux in, if you remember Fourier's law, will be equal to Qx, which is equal to minus K, the conductivity, multiplied by our temperature gradient. So what we're saying here is that the heat flux in, and this has units of watts per meter squared, our heat flux in is simply equal to some constant, the conductivity, multiplied by our change in temperature by x. And by the same logic, because we've applied Q at x equals 0 here, we need to apply Q at x plus dx, which is going to be here. So therefore our out is going to be equal to, well, Q out, which is at the end of our control volume, and that's going to be equal to, again, minus K, but this time multiplied by the temperature gradient at the outlet, which we've already written here. And we know that that's dt by dx plus d2t by dx squared multiplied by a small change in x dx. Right, so what we've defined here is our inlet and our outlet heat fluxes. So now let's define our change. Our change is going to be what you know from basic thermodynamics, and that's going to be that delta Q, which is the heat within the control volume, is going to be equal to mCp delta T. And that delta T is the change in temperature between the outlet and the inlet. Now, we can rewrite this as the density multiplied by the volume. That's going to give us our mass. So the density multiplied by the volume, because we defined the area as A, the volume is going to be A multiplied by small delta x. So that's m. So this is our m, our mass term. That's multiplied by Cp delta T. Now, this has units of joules, whereas our in and out terms have units of watts per meter squared. And so what we're going to have to do, and you'll see, is we're going to have to multiply our flux, or our surface flux, by an area and by a change in time. So what we'll do is we'll write out what this means. So what this means is our in minus out is going to be multiplied by an area and a small change in time. So let's write this out. We're writing our in and out terms now. So that's minus K dt by dx. And I might run out of space here actually. Minus our out term And this is going to be equal to our change in heat, which is equal to rho a small delta x Cp, I'm just going to fit this in, delta T. So we've got our in, our out, and our change. Right. So this is where we need to start rearranging this equation into a form that we can more understand. And so you'll immediately see that if you distribute this k between these terms, that this term and this term are going to cancel out. And so what you'll be left with is, oh, and you also notice that the areas actually cancel here. And so if we distribute the delta t and cancel this minus k dt by dx term, what you'll be left with is, what you'll be left with is k d squared t, or d2t, by dx squared multiplied by our small change in x multiplied by a small change in time is equal to our rho times our small change in x Cp delta t. And so you'll see from here as well immediately that this small change in x is going to cancel out. And so what we're left with is k d2t by dx squared multiplied by a small change in time is equal to rho Cp delta t. Now, what I'm going to do is I'm going to group k, rho, and Cp onto one side, and I'm going to group delta t and small delta t on the other. So what we're going to get is d squared t d2t by dx squared multiplied by the terms that we've grouped. And that's going to equal our delta in temperature divided by some small change in time, delta t. And what we can do now is take the limit as delta t and small delta t go to 0. And that is going to equal the derivative of t with respect to time, or the derivative of temperature with respect to time. And if we substitute that back in to our previous equation, you'll see that we get this d2t by dx squared multiplied by k over rho Cp is equal to the derivative of t with respect to t. And this term here we often group into something called alpha, or the heat diffusivity. And so if we group this, you'll see that the final heat diffusion equation that we get is the second derivative of temperature with respect to x multiplied by the heat diffusivity equals the first derivative of temperature with respect to time. This is the heat diffusion equation in one dimension, and I'll be going through some of the solutions to this equation in later videos. Thanks for watching.